All right, so today in this probability review session, I think I'll be going through 6 questions. Let me see, 1, 2, 3, 4, 5. 5 questions, and I'll talk a bit about the binomial distribution and how that comes about. And just to reiterate, these questions and like probability in general, I would say not something that data scientists face on a day-to-day basis. It's more for interview questions. Just some companies like to test the way that you think about probability and your thought processes through these questions. So that is why we do talk about it in this program. And that's why we have these questions for you to solve. So something I like to do during these sessions is mostly just show you, like, I guess, little tips and tricks that I use to like break down probability questions. I will preface this by saying I've been doing probability for years and years. And like I've drilled maybe like over 100 of these kind of questions throughout my life. So I think a lot of it does come from experience, but hopefully just like knowing what are the little things to look out for and the little things that, you know, can make solving the problem easier. That's kind of what I want to show you all. But yeah, as usual, any questions at any time, feel free to interrupt me. First question I wanted to talk about was set theory, which in this question includes the inclusion-exclusion principle. This was a question that I think I went a little bit into when we did our probability study group, but just want to talk it over again really quick. You recognize a set question whenever you have, you know, usually you have 2 or sometimes 3 different events happening and they have some sort of overlap. So if you see something like an overlap, and in this case, this is the Visa Amex example. And really quickly, here we randomly select customers and make notes of whether a customer owns a Visa, an Amex, or both. And these are the probabilities that arise. You have like 0.5 for having a Visa, 0.4 for having an Amex, and then 0.25 for having both. And so like a very major sign that this is going to be a set question is you have, you know, the probability of both A and B. And so very likely with these kinds of questions, what you will be computing is, you know, any probability that isn't provided is fair game. Like for example, like what is the probability of A that isn't B? Or what is A and B inclusive? And what is, I don't know, a lot of different conditionals can come out of this as well. But just to go over, I think I did this as well during the study group. Whenever I have this kind of question, I really like to draw a diagram. Very likely when you're doing this kind of question, you will be giving pen and paper. A lot of the technical interviews that I've had, when it was in person, I had a lot of a few technical interviews where they actually provided me with pen and paper to do like my scratch work. And of course, now over Zoom, you can have your pen and paper with you. So with this kind of question, what I like to do is start with a Venn diagram. So here, let's just take note of these numbers. A is Visa, B is Amex, A is 0.5, B is 0.4. Both A and B, which is what we're given, is 0.25. And so I already have this here I have this Venn diagram I've created here. And what I'm going to do is I'm just going to fill in the Venn diagram with numbers. So what I like to do here, all of A is 0.5. Let me just do a quick copy paste here. B is 0.4. And the other number they gave us was the middle, both A and B, being 0.25. Now that we have these numbers, what I like to do is I want to simplify and fill in as much of this diagram as possible in the way that makes most sense to me. And so for me, what I like to actually fill out is I like to fill out each individual area just so that there are no overlaps. And so whenever I need to calculate any probabilities, it's a matter of just summing up the small parts. What I mean by that is here we're given 0.5 and 0.4, but that doesn't account for this overlap here. So I actually want to write out all the numbers of each individual space. So what I mean by doing that is here, you know, we have this whole A bubble being 0.5 and this middle section being 0.25. I actually, instead of labeling this 0.5, I actually want to know what is this crescent shape here. And I would just fill that up with 0.5 minus 0.25 because that would be the part of A that doesn't intersect with B. So I'll fill that with 0.25. And very similarly, fill this up with 0.15, just so that this doesn't need to be here. And then finally, now that we have, all the area that's in the bubbles, we just compute what is outside of the bubbles. And so I believe this is 0.65, and this we can evaluate to be 0.35. And now this just makes the rest of the process a lot easier. If I want to find like any subset of anything, I could just compute probabilities with numbers that are already on our page. So let's see what they asked for. Compute the probability that a selected customer has at least one credit card. All right, that's pretty straightforward since we already have this here. And let me just make a text box here to take notes. So has, what was their exact wording? At least one credit card. All right, so probability at least one credit card would, based on our diagram, just be the sum of the three areas that are in our Venn diagram. So it's just this entire part. So what that is 0.25 plus 0.25 plus 0.15, which is 0.65. And so that, because we have already labeled all the parts of our diagram, makes it so much easier. If you're wondering, all right, how would we do this with the inclusion-exclusion principle, which is this one over here, meaning like how would we do this with the probability formulas? We would do it more, more formally by finding A union B, because what we're doing here is we're finding A union B. And the formula for that is probability of A plus the probability of B minus the probability of A intersect B. And if we fill in the numbers, it actually all comes out to 0.65 as well, because we have A and B being 0.5 and 0.4. And then we minus that middle part. And the middle part is still the same here as 0.25. And we end up at 0.65, right? Because this is 90, this is 25, ends up at 65. So this is the answer to the first problem. The next thing that they ask for is the probability a selected customer doesn't own any of the credit cards. And again, very simple, because we already labeled it here. The part that isn't in any of the bubbles is 0.35. If you want to do it formulaically, because we did this part already, A union B is 0.65. We want to do what is the probability of A, actually more specifically, it would be A union B complement. So anything that isn't A union B would be 1 minus what we just calculated, 1 minus 0.65, which is 0.35. So that's our second question, which is probability of neither credit card. Let me just write that down. There we go. And the last question here is the probability that a customer only owns a Visa card. And here, and I do want to talk about a conditional right after this, but here, again, because we already have that, A has a part that is only A and has a part that is A and B. And so here we're just looking at the part that is only A. We know that to be, let's see, 0.5 minus 0.25, which is 0.25. Now, what if the question was asking, what is the probability of someone owning only a Visa card, given that they already own a Visa card? Just to reiterate, that question is slightly different because there we have a conditional probability. So what if we wanted to find, what is the probability someone only owning a Visa, given that they have a Visa? So that is kind of similar to only A, but in this case, we're only considering it out of the subset of people that have a Visa. And we'll get into more conditional probability in, I think, in a few questions from here. But I just wanted to note that in conditional probability, I sort of like to think of it as you're segmenting your sample space. In this case, this probability of only A, our sample space was the entire, the entire population of people sampled. But here, our sample space is only the people who have a Visa. And so I like to think of this as the denominator being people who only have a Visa. And so what I like to do first with conditional probabilities that are already laid out like this, first create the denominator, which is 0.5. And so this conditional probability is really asking what proportion of visa holders only hold visas. And so thinking about it like that, I sort of think, all right, out of this bubble, what proportion is this crescent part? And feel free to interrupt me if that doesn't make sense, but that's how I like to think about it, which is how I arrive at 0.25 out of 0.5, which will give you half, or 0.5 again. Questions on this problem? I would say this is one of the easier ones, especially if you were to draw it out. Cool, awesome. I'm happy to like circle back to any of these at any time as well. All right, the next one I wanted to talk about, this one usually comes up a lot in one-on-one, so which is why I wanted to talk about this one. So this, I don't know how many of you have gone through the lessons, but there is a question where you have your iPhone access code, which is like a 4-digit code, and then someone's trying to like hack into your phone. What is the probability that they get in? So that's like the setup, the problem. In this sub question, your iPhone access code has 3 different numbers, 2, 7, and 8. And the thief knows that one number was reused. And I think they set it up by saying like your fingers were greasy and then you have like your little fingerprints on 3 numbers. You had your fingerprints on 2, 7, and 8. And so therefore the thief knows that, you know, you have a 4-digit code, but only the numbers 2, 7, 8 are used. So one of the numbers were reused, but doesn't know which one. So what is the probability that the phone will be unlocked successfully? I think in this problem, they also say that you have 5 tries to unlock the phone. And so numerator straight away will just be 5. And this, what I want to get into more is the calculation of the denominator in this problem. How many possible phone combinations, phone access code combinations are there with 4 digits that have the numbers 2, 7, and 8? I think this one, people just have like trouble figuring out how to think about it. And I'm going to share the way I think about it. That will hopefully help. So let me make this a little smaller so I have some space here. So I just want to think about one of the scenarios first. I don't know which number is repeated. So let's just assume the number 2 is repeated first. So with the number 2 repeated, the second thing I like to think about is what if the 2s were distinguishable? And what I mean by that is instead of having, you know, just 2278 as a passcode, instead of 2278, let's think of it as 2A, 2B, 7, and 8. This just helps us with the counting as a first step. So here we have 2A, 2B, 7, and 8. Another possibility, maybe we have 2A, 7, 8, 2B as a different possibility. Actually, let me like not put these commas here. There we go. And then just as another example, maybe there's like 8, 2A, 2B, 7. And these are just possible passcodes. And so knowing that 2A and 2B are distinguishable, how many different 4-digit passcodes do we have here? Given that we know that let's assume that the 2s are distinguishable, how many ways can we arrange this? And when we're dealing with, you know, just arranging these objects, the number of combinations we have here is just factorial 4. Because we're just arranging 4 distinguishable digits and seeing how many ways they can be arranged. And more specifically, it is the number of 4-digit permutations. There we go. And so we have this, but here what I did was I assumed that 2A and 2B were distinguishable. And so we're gonna undo that. So within this factorial 4, we have these combinations, but we also have situations where, you know, we have the A's and B's flipped. So essentially what we did, we have double counted every single possible combination just because we had assumed that 2A and 2B were distinguishable. So to deal with these repeated digits, we have to divide our factorial 4 by 2. So we end up here at factorial 4 divided by 2. Now, we're lucky that here is only 2, but technically, if we had, if we, let's say, for example, had 2 being repeated 3 times, so let's say we only had like 3 2s and a 7, we actually would have to divide it by 3 factorial. So instead of 2, this more specifically should be 2 factorial, which just happens to evaluate to 2 as well. So taking into account repeats, we have to divide by number of repeats factorial. Or actually, let me do it this way instead. Number of repeats. And this usually holds for any problem with a repeated digit or a repeated whatever it is. So now that we have this step, there's one more step, because here we had the 2 being the repeated digit. Let's think about, all right, what about if the 7 was a repeated digit? So factorial 4 divided by factorial 2, that's a total number of combinations of numbers with the 2 being repeated. So taking into account, all right, what if 7 was repeated? We can actually do all of the same math that we already did up here and come up with factorial 4 divided by factorial 2 different iPhone combinations. And then same for if 8 was repeated. If 8 was repeated, it's another factorial 4 divided by factorial 2 different passcodes. And so therefore we end up with the total number of 4-digit combinations being 3 times factorial 4 divided by factorial 2. So that, I believe this is the denominator for this question in the lesson. I believe, just to reiterate, in this question, there are like, I think you have 5 tries to unlock an iPhone. And so the answer to this question would technically be 5 out of 3 divided by factorial 4 divided by factorial 2. So this should be the answer to the final problem. Cool. Any questions on this one? All right, the next problem is a combinations problem. Combinations one, less common, I will say, but also good to know because it does present a really good use case for the combinations formula. So let's get started with setting up the question. So here you have 6 different consonants and 4 different vowels written on pieces of paper in a bag. And the idea here is you're going to draw 5 letters out of the bag. So the first question is asking, what is the probability that you draw exactly 2 consonants and 3 vowels when drawing 5 letters? So here we actually have to set up both the denominator and the numerator, because you know your sample space here is you're drawing 5 letters, and your event space is drawing exactly 2 consonants and 3 vowels. So we need to actually do both of those parts. So for the first part of this question, let's actually start with the denominator. How many ways are there to draw 5 letters out of 10 letters in a bag? And in this case, with the denominator, doesn't matter consonants or vowels. So we're just looking for the number of 5-letter combinations you can get here. So the number of 5-letter combinations is equal to 10 choose 5. And 10 choose 5 is just another way of saying this formula. Oops. This formula over here, the combinations formula. The number of ways of choosing 5 out of 10. So number of 5-letter combinations is 10 choose 5. And I'm going to write it like this because it's easier to type out, but it really translates to this formula. All right, so now that we have, this is our denominator. Now we need to look for the number of ways to draw exactly 2 consonants and 3 vowels. So 2 consonants and 3 vowels, let's do them separately. First, let's look for the number of ways to choose 2 consonants out of 6 consonants. So number of ways to choose two consonants of 6 is actually equal to 6 choose 2. And very similarly, number of ways to choose 3 vowels out of 4 is 4 choose 3. And all we have to do to put it together, the number of ways of choosing 3 vowels and 2 consonants is just the product of these two. Because with every possible 2 consonant combination, you can get any of the 3 vowel combinations and make them and basically pair them up in those ways, which is why we can multiply these two to get the total number of ways to draw 2 consonants and 3 vowels. And so therefore, the probability for this question, which part A, let's just go with A, equals to 6 choose 2 multiplied by 4 choose 3 divided by 10 choose 5. And that should give you your probability. Not going to do all of this math out, but you should be able to Python it out and that'll work. Questions so far? All right. Okay, so next question. Out of 6 consonants and 4 vowels, how many words with 2 consonants and 3 vowels can be formed? Which I think we actually already did that. Out of 6 consonants and 4 vowels, I see. 6 consonants and 4 vowels, how many words with 2 consonants and 3 vowels can be formed? So we've already sort of gotten started on this question. So we already have this part here, which is the number of ways to choose 2 consonants and 3 vowels. So let's actually put it in a different text box here. Number of ways to choose 2 consonants and 3 vowels is equal to 6 choose 2 multiplied by 4 choose 3. Now, in this example here, we have only chosen these. So if you remember, when you choose things, the order doesn't matter. So for example, if I have 2 consonants and 3 vowels, so let's say I have the word B, C, A, E, I. Yeah, 2 consonants, 3 vowels. In this case, B, C, A, E, I, and the word B, C, E, A, I here are considered the same because we used combination formula. So in this number here, these words that we form, and in this case, they're asking for words, but I don't think they care about which are actual dictionary words or not. But here, these 2 words here are counted as the same because we use the combination formula. Because in the combination formula, order does not matter. But with words, order does matter. So from here, we have to think about, all right, with each of these unique 5-letter combinations, how many ways can I arrange each one? So within the letters B, C, A, E, and I, how many different words can be formed? And in this case, again, dictionary words doesn't matter. It's just really the number of ways to arrange the 5 letters. So the number of ways to arrange 5 letters is back to our factorial formula. So number of ways to arrange 5 letters is just 5 factorial, or I'm actually going to write factorial 5. So now we sort of have to put this together. The number of ways to arrange 5 letters is factorial 5, and the number of 5-letter combinations that we have is here, 6 choose 2 multiplied by 4 choose 3. So therefore, the number of words with 2 consonants and 3 vowels is the product of these two. It is factorial 5 multiplied by 6 choose 2 multiplied by 4 choose 3. Cool. And there we have it. I think that is the answer for E. All right, any questions about this one? Awesome. All right, well, the next one we're gonna talk about is also a little bit tricky, but this one is one of the ones that I have like a little trick of like making it a lot easier to solve. So here, there's the example where 2 dice are thrown. So given that at least one of the dice has come up on a number higher than 4, what is the probability that the sum is 8? And so I think the part that trips people up is this part. One of the dice has come up on a number higher than 4. What's the probability that the sum is 8? And in the question, they actually set up events A and B. So let's just use these events that were given in the problem. So event A is going to be when either I or J is 5 or 6, because higher than 4, strictly higher than 4, so it's only 5 or 6. And then event B is when I and J equals to 8. So in this case, we can assume that like I is the outcome of one dice, J is the outcome of the other dice. And then event B is when the sum is 8. So for something like dice throws, where you have like a pretty smallish number of outcomes, what I like to do is really draw it out in diagram. I think y'all have seen with like the Venn diagram example earlier, I think that drawing diagrams just makes things a lot easier because it's very visual rather than having to think of formulas. And I think the solutions here does go pretty into formulas. All right, so what I like to do here, because we have 2 dice, I think the easiest way to present this information, I mean, there are many different ways to do this, but I like to do this in a table. So let me make this all smaller. And let me draw this table. Let's see if I can do this. Table here, and we have, let's see, let's do a 7 by 7 table and see how this comes up. All right, so I have this table over here. And I'm gonna have rows representing one dice, columns representing another dice. So what I mean by this is gonna be the outcomes of one dice from 1 through 6, and then here, 1 through 6 as well. And let me just color it in so it looks nice. Let's go with this for now. All right, so, oops, what did I just do? There we go. So I'm gonna have each of these cells represent an outcome. So for example, this cell is when you have dice, the first dice being 1, second dice being 1. This one will be 1, 2. This will be 1, 3, so on and so forth. And this will be like 2 and 1. So on and so forth, all the way till we get to 6 and 6. So the first part that they ask is, what is the size of the sample space? So sample space, you have 2 dice, each of them have 6 different outcomes. Sample space is pretty straightforward, just 6 times 6, 36 possible outcomes when you're rolling 2 separate die. So I think that one's pretty straightforward. We can put it here as 6 times 6, 36. Next one is A intersect B. So when they're asking for intersect, we should actually map out what our A's and B's are. The way I like to do this, let's actually color code these cells. So let's do event A first. Either I or J is 5 or 6. Let's just go with, I guess it doesn't really matter, but let's go with like, this is I, this is J. So let's look at I first. If I and J are 5 or 6, that is all of these outcomes. So let me color this in one color. I is 5 or 6, all of these outcomes. Now, J being 5 or 6 is going to be all of these outcomes. And here it's going to look very symmetrical as well, something to note. But this is your event A. This is your event A of I or J being 5 or 6, which, you know, having this mapped out makes it a lot easier than going into the conditional probability formulas. And next up, we have event B, which is all the situations where I plus J equals to 8. So, all right, I plus J equals to 8. That can happen with, I think the first one we can think of is 6 and 2. So with that, let's do 6 and 2 is here. And then because it's symmetrical, we have 2 and 6. Oops, just do here. 2 and 6 being here. The other one that sums up to 8 is 5 and 3. So we have 5 and 3 here, and we have 5 and 3 here. And technically we also have, oh, actually, just to be more specific, we'll do 3, 5. And finally, we also have the case of 4, 4. So these are all the cells that you can add up to 8. So let's actually quickly color in these as well. Let's color these in green. I'm gonna do this one green, and this one blue, because blue and yellow make green. All right, is that blue? That's not blue enough. There we go. All right, so here, what is the probability of A intersect B? A intersect B is just gonna be the overlap of the blue and the yellow. So because the overlap of the blue and the yellow make green, it's just the green ones. So actually, let me just write more clearly. A is yellow, B is green, no, B is blue, and then A and B will be green. There we go. So A intersect B, here you can see there are only 4 squares that are green. So it's just gonna be 4 out of 36, which goes down to 1 out of 9. So the probability of A intersect B, which is here, the probability of having, you know, either I or J being 5 or 6 and I and J equals to 8, 1 out of 9. Questions on this part so far? All right, awesome. So now they're asking, what is the probability of A? And so A, as I mentioned, is all the yellow parts. And all the yellow parts, I mean, you can count up all the squares, but that gives us, let's see, what is this, 20? Is it 20? 1, 2, 12? Yeah. So here we have 20 out of 36. And so that's the probability of A, which is pretty straightforward because we have filled in this table. And then now they're saying, use the above to calculate the probability of B given A. So this requires a little bit of formula, I think. The probability of B given A has a conditional probability of the probability of A intersect B, or actually more specifically, it would be B intersect A, but in this case, it doesn't matter, divided by the probability of A. So this is the conditional probability formula that we're actually going to talk a little bit more about on Thursday. But this is how you would use it. I would say the conditional probability formula is a good one to remember for interviews. But yeah, so since we actually have both of these probabilities, we have both B intersect A, which we have as A intersect B, but same thing, divided by this, it comes out to, let's see, I think it's easier to use the 36 number because we have that there. 4 out of 36 divided by 20 out of 36, which evaluates to 1 out of 5, or 0.2. And there we have it. That is the conditional probability for this question. Questions about this one? All right, nice. We're making good headway. Last question that we have before we talk about the binomial distribution is this question. This one is requested by Sarah. So if anything needs to be clarified, please let me know. Here we have a 2-card hand drawn from a standard playing deck. And I actually think the second question is a little easier. So, but let me actually talk about both situations first. So the first question here they have is, what is the probability of drawing 2 aces, given that we know one of the cards is an ace? This is a little hard to frame, so I'm going to explain that a little bit more later. But let's first talk about this one that I think is easier. What is the probability of drawing 2 aces, knowing that one of the cards is the ace of spades? So I like to think about conditional probability, as I've mentioned, as like a subsetting of your sample space. So here, your sample space is a situation where you have already gotten the ace of spades. So you've already gotten the ace of spades. What is the probability of, just getting one more ace? So the way I like to outline this second question, so let me do it this way. Probability of 2 aces given that we have the ace of spades. So I like to think of it as I already have the ace of spades. And actually, let me see if a Venn diagram might help a little bit better. All right, so in this Venn diagram, we have this bubble here, and this bubble is going to represent 2 aces. Let me see if I make this transparent. There we go. This bubble is going to represent 2 aces. So if you have 2 aces, what is the probability of getting an ace of spades? So having both our aces and ace of spades is actually a subset of this. I don't know if this is more helpful. I think let's stop with this Venn diagram thing. But anyways, I'm going to continue explaining this. The probability of having 2 aces, given that you already have the ace of spades, you already have the ace of spades. You have 3 aces left in the deck of cards. And so 3 out of the 51 remaining cards are aces. And so that's why I'd say this one is a little bit simpler to think about. You have 3 cards left out of 51, 3 aces left out of 51 cards left, which is why we end up with 3 out of 51, which is 1 out of 17. So I think that one's a little bit more straightforward. Let me delete this. That's something really better.
Ish, when you, I don't know, like kind of in the last problems, I guess we thought about it as like when you have a condition of like given A, that it's a subset of like A is now your like probability space. And then you take like just the proportion that's in, that they intersect in.
That's right.
So wouldn't it be that divided by the probability space of like drawing the 1 ace first? Because the probability of drawing the ace of spades is like 1 over 52, right? So then would it not be the probability of drawing the ace of spades within that 152? I don't, that's like kind of how
Gotcha. Yeah, I see where you're getting at. I see where you're getting at. For, let's see, how can I explain this? I see what you're saying, because usually with the probability formula, you would be looking at 2 aces intersect with the ace of spades, right? And then multiplied it by, and sorry, divided it by the probability of getting the ace of spades.
Yeah, that's like at least how I was thinking of it.
Gotcha. Let me see if I can like we have to dissect this part. This is the part that like needs a little bit of this dissection, I think. So 2 aces and the ace of spades divided by the ace of spades. I would say, so that's kind of like the part that, like personally, a lot of these probability formulas are actually the thing that do trip me up. Because, you know, you apply the formula and sometimes, especially when it's these like situational things and it isn't just straight up numbers, it's hard to like interpret this. Like what would you even like interpret that as? So let me think. I would probably do it as getting the ace of spades is 1 out of 52. And so that is this part. And you want to multiply it by getting, sorry, ace of spades is this part. And then you want to intersect it with this part, with getting 3 other aces. Sorry, by getting 1 other ace out of the 3 possible aces that are left. So I would probably think of that as, probably honestly, like I would think of it as 3 out of 51, right? So here you get the ace of spades and then the probability of just getting another ace.
Right.
So with this, we're going to divide it by the probability of getting the ace of spades, which is oh yeah, okay, so this one works out. So it's the probability of getting the ace of spades again. You can see that the 1 out of 52 part cancels out.
Okay, yeah.
I do think that this, coming up with this number in this context is a little bit harder than doing it if you like just think of, all right, I already have the ace of spades. What is just the probability of getting the next one to also be an ace?
Okay.
But this one happens to work out. But it does take, I will say this one just takes a little bit of like thinking how you formulate, how you get this part translated into these numbers.
Okay, gotcha.
Yeah. The next one is a little bit tricky, or I guess like the one before.
Yeah, I had trouble understanding what they did up there. Like the 4 choose 2 divided by the 52 choose 2. Like where they got that, I guess.
Yeah. So here, I think the second question might be one that the Venn diagram helps a little bit. So I wish I didn't delete that, but let me bring that back. So here I have a Venn diagram. Let me just, doesn't have to be big, so let me make this smaller. So here's gonna be the situation where you have one ace, because this is your given. So this is gonna be one ace. Now, every situation where you get two aces is going to be, you know, a subset of getting one ace. I don't know if that makes sense. If you get two aces, means you already got one ace. So therefore, I actually like to draw like a second bubble within this, saying that, all right, this smaller bubble is the situation of getting two aces. That makes sense? So now that I got this conditional probability that we're trying to find is this small bubble out of this bigger bubble. So this bigger bubble is going to be our denominator, and this smaller bubble will be our numerator. So that's the way I like to set up this question to make it at least make more sense to me. I guess this doesn't need to be so wide, so let me move it over so I have space. There we go. So just to reiterate, the probability of drawing two aces, given that we know one of the cards is an ace, I represent it in this Venn diagram where one ace is this big bubble, and because every situation that you have two aces, you already have one ace. So therefore, two aces is a bubble within the one ace bubble. And I see my two aces as the numerator, one ace as the denominator. And I think having that, I guess, perspective to this question makes setting up the math a lot easier. So first we can start with the numerator. So with the numerator, they use probability here. I just like to do like number of ways. So I like to think of number of ways to get two aces. And because, you know, in a standard deck of cards is out of four aces, is really just 4 choose 2. And then with that, we want to think about the denominator. And one thing that is a little bit tricky is the denominator in this case kind of includes the numerator, right? The denominator includes the numerator because every situation where you have one ace, you have two aces. So I think that's the part that's also a little bit confusing here as to like, why do they do one minus neither? You're just looking at all the ways that you get at least one ace. Because given that we know one of the cards is an ace, those situations, you can have still just one ace. Like if your second card drawn is not an ace, you still have one ace. But if your second card is an ace, you get two aces. So technically, this denominator is looking at the number of ways to get at least one ace. Which, as a problem, as like the solution here has it, is the number of ways to, they do it as 1 minus the number of ways to get no aces. And that's given by number of ways to choose, let's see, non-aces, it's 48. And here you're choosing 2, so it's 48, choose 2. And so therefore the probability of literally like both aces given one is ace is given by numerator over denominator, 4 choose 2 divided by 48 choose 2, which I guess based on what I see there, it values to 1 out of 33. I guess similarly, I do want to think about it in terms of this formula. So let's see if we can do that. Now that we have this here, let's see. If we break up that formula, we're looking at the probability of both aces intersect one ace. And it's going to be divided by probability of having one ace. So the probability of both aces intersect one ace, if you think about the intersection here, given this diagram, the intersection of this one bubble and the two bubble is just the two bubble. So it's actually still the probability of both aces divided by the probability of getting one ace. And I think here we actually have to be more specific by saying at least one ace. Because, more specifically because, if we just have this to be one ace, these won't intersect, whereas this has to be at least one. So this will be probability of both aces divided by probability of at least one ace, which I think this all matches up. 4 choose 2 divided by 48 choose 2, and it'll give us the same answer of 1 over 33 that way. Hopefully that helps. I think it is worthwhile thinking about it. With this second part, worthwhile thinking about it this way because it does simplify the problem a lot more. But with this problem, this one is a tricky one on purpose. This is like a question that has been asked in like pretty much every college probability like midterm. So yeah, that's a pretty common one to think about as well. But I personally like this diagram. I don't know about you all, but hopefully it's helpful to think about that way. Any questions about this? All right, well, I wanted to end off with binomial distribution. I didn't talk about it during study group because I think in that topic 12, there are more important things than the binomial distribution, but it is a very interesting one to think about for sure. So this is an example where you would use the binomial distribution. So I think I gave this exact example. I think I gave it as like basketball. So given that you have a probability of 0.8 of making a shot, what is the probability you make 2 out of 3 shots? So if we remember binomial distributions, so when we're talking about normal distributions are defined by their mean and their standard deviation. But for a binomial distribution, it's actually defined by the number of trials and your probability of success of a single trial. So just to know, like different named distributions are defined by different parameters. Normal distribution, you have your mean and your standard deviation. Binomial distribution, you have number of trials as well as your probability of success. So actually, if you wanted to write this out in I guess scientific notation, you have X is represented by a binomial distribution of, they usually start with number of trials, which here it's 3. And here you have the probability of success, 0.8. More specifically, you can do n equals to 3. Probability is 0.8. So this is the formula for a binomial distribution. Q, as you can see here, is actually 1 minus P. X would be, in this case, X is 2 because we're looking for the probability of 2 out of 3 shots. And if you plug all the numbers in, you will get the answer here. But I wanted to break down where this equation comes from. I think it's very interesting and good to know sometimes. So, all right, here we're making 2 out of 3 shots in basketball. Let's first think about what are the different ways you can make 2 out of 3 shots. Different ways of making 2 out of 3 shots. Because it's only 3 shots, let's actually do like ticks and crosses, which I'll use the letters V and X, V being a tick and X being a cross. So, all right, 3 shots in basketball. let's say you make the first two and you miss the last one. That's one way to do it. Let's say you missed the second one, and then the other thing is you missed the first one. So these are the 3 different ways you can make 2 out of 3 shots. And this actually translates to, like the number of these ways actually translates to 3 choose 2. Because it's the number of ways of choosing 2 successes out of 3. Very interesting mathematically, I think, because of the way this formula works, especially in the denominator. 3 choose 2 is actually equal to 3 choose 1. Because here you can see you have n minus x and x. So 3 minus 2 is going to be 1, and then we have 2 itself. And so whichever way you have it, as long as these 2 numbers add up to 3, if you switch them around, it actually values the same thing. If what I just said doesn't make sense, don't worry about it. But if you had a bigger example, so let's say out of 10, 10 choose 7 is actually equal to 10 choose 3. And similarly, like 10 choose 6 is equal to 10 choose 4. So that's what I mean by it's like kind of symmetrical in this way. It evaluates to be the same amount as long as you have these numbers, 1 adding up to 10. Yeah, as long as these 2 numbers add up to 10, they're equivalent to each other. But that's less important for this. So here we have 3 choose 2 ways of making 2 out of 3 shots. Then we bring in the probabilities. Making 2 shots and failing at 1 shot, the probability of that is just 0.8 multiplied by 0.8 because 2 successes multiplied by 1 failure, 0.2. And this is where this second part of the formula comes from. So this factorial part comes from the number of ways to do it. And this second part just comes from multiplying the probabilities together. And so we can actually put this as P, what is the shortcut to do superscript? I don't remember, I think it's this, nope. This one, there we go. P times number of successes, and our number of successes is given by 8, given by X. And then we have, let's see, multiplied by 1 minus P to the power of n minus X. So that's where that comes from, because n is the number of trials, X is the number of successes, so number of failures is n minus X. So that's where that part of the formula comes from. And so putting that all together, for any binomial, we're looking at, the number of different ways you can get X successes out of n trials, and then taking the product of all the probabilities of the successes and failures. And that's where this formula comes from, which actually works out really nicely. I think there is one lesson in the binomial distribution labs that you are asked to actually like code out this formula. And I think they actually have you plot out a PDF, which is also pretty cool, I think. But yeah, we're actually pretty good on time. Hopefully this was helpful. Does anyone have any questions related to probability? We are going to do more probability in topic 17, which is Thursday's material. So let's get ready for that. But awesome, this recording will be posted. I would say like for this stuff, you don't really have to get into it now. I would say if you are gunning for, I would say like if you're preparing for interviews, I would then come back to this. And also depending on the kinds of jobs that you're looking for, it would probably be more like mathy roles that require or that will ask you probability questions. So just so you all know, not every interview for every company is going to include probability questions. So there's a good chance that you might not even have to study these. But they're always good to know. I think for some general interviews, they will come up. I would say probably not something as complicated as this, but something like this probably will come up. And there's also one very common one that I didn't talk about here because it's more related to topic 17 that I'll talk about on Thursday.
Ish, do you have any resources for practicing problems like this? Kind of like how they have SQL sites where they do little practice problems. Is there
Yeah,
anything like that?
I will say, because like probability is more of like a pure math thing.
Mm-hmm.
Um, Honestly, something that really helped me was just like doing all these questions in college. So literally
Yeah.
just look up like college like probability courses. A lot of them have their homework solutions on as like PDFs online somewhere.
Okay.
Um, I can try to look some of like my old ones up as well. But I know like some schools that have good ones, like Duke University has a set of really good ones. I'm pretty sure Stanford has some of theirs. MIT, they have their open course where they have their homework up as well. Those I say will all be on the harder end. Those will be like much more on the harder end of the questions that they would probably ask programmers, but good ones to practice because they do force you to think about probabilities from like different perspectives. But yeah, personally, I don't have any like code friendly resources. Definitely those, and also I think something else to reiterate is if you can do it like pen and paper, probably better than if you can do it by code. I think like once you do it by pen and paper, translating that into like equations and code is going to be that is the easy part, I think. But cool. Hopefully this was helpful. I personally really like solving probability questions. I just did it for a lot of semesters, so I enjoy it. Stockholm syndrome probably was what happened. But yeah, if there are any other questions, just let me know. But if not, I will see you all starting tomorrow's study group. I did put a bunch of new stuff up on the homeroom, so do take a look at that. Huge focus on topic 18, which only comes on Friday. So I will say that like if any of you are feeling like overwhelmed by statistics and like don't want to do it anymore, skip to topic 18. I do recommend doing that, yeah, because topic 18 is a lot longer and is more directly relevant to data science. So if anyone feels short on time or just doesn't want to do stats anymore, definitely just skip to 18 and we can talk about it on Friday. All right, well, have a good rest of your day, everybody. Hopefully this was helpful. I will post this recording for your reference in the future. But yeah, bye.
Thank you. Bye.
You're welcome.